topic of today's video will be solution of Bessel's equation. And like we have seen in our last videos that a Bessel equation has a singularity, or we call it regular singular point at x equal to 0, right? So we have to use Frobenius method this time, right? So I will start with that Bessel's equation, and that is of this form. Bessel's equation, that is x square y double dash plus xy dash plus x square minus p square multiplied by y equal to 0, right? So this is called Bessel's equation, and this p is a constant here. I will write it where p is a non-negative constant, right? We will call it equation number 1, and as you can see that the coefficient of y dash and y are 1 by x and x square minus p square over x square, and they have a singularity at x equal to 0, right? So clearly x is equal to 0 is a regular singular point of px equal to, that is the coefficient of y dash, and that is 1 over x, and qx is equal to x square minus p square over x square, right? And you can verify this fact by just multiplying this px with x, so that you will get it is 1, and this will be x square multiplied with qx, that will become x square minus p square. So ultimately px and qx will become analytic at x equal to 0, right? That's why we are calling it a regular singular point, right? So start with, I have to use that Frobenius series, right? And that is of this form. Suppose the solution is of the form y is equal to summation n equal to 0 to infinity an x to the power n plus r, right? And if I write it in expanded version, then it should be like this: a naught, I should write x to the power r outside, and a naught plus a1x plus a2x square, and so on. And you know that this a naught is not equal to 0, right? And be careful at this point, because we already had one constant, that was p, and at this step we have already introduced two new constants, n and r, right? N is the index for summation, and r is the variable to be determined, right, by the auxiliary equation, right? And now I will differentiate this to obtain y dash and y double dash, in order to plug those values here in my equation number 1. So I will differentiate it. On differentiating, y dash is equal to summation n equal to 0 to infinity an n plus r multiplied with x to the power n plus r minus 1. This is the first derivative of y, and similarly obtaining its second derivative, that will be summation n equal to 0 to infinity an n plus r n plus r minus 1 x to the power n plus r minus 2, right? And remember that while differentiating a Frobenius series, the range of the summation is unaffected, right? While in case of power series, it gets affected, right? Okay, now I will plug those values y, y dash and y double dash here in my equation number 1, right? So plug y, y dash and y double dash in differential equation number 1, and that will produce, if I multiply this y double dash with x square, then this power will be reduced to x to the power n plus r, because you have already here n plus r minus 2, and you are going to multiply it with x square, so it will be reduced to summation a n plus r and n plus r minus 1 x to the power n plus r, right? And the range again will be unaffected. As you know that if you multiply a Frobenius series by any power of x, the range is again unaffected, right? So this will be your first term, and then second term will be x multiplied with y dash. So this is your y dash, you have to multiply it with x, so you will get summation n equal to 0 to infinity an n plus r x to the power n plus r, right? And see here you have two terms actually. The first term is x square multiplied with y, and then p square multiplied with y. So I have to write two terms separately. The first will be x square multiplied with y, that will produce summation an x to the power n plus r plus 2. The last term will be p square. Since p square is constant, so that will appear outside the summation sign. Summation n equal to 0 to infinity and y is an x to the power n plus r equal to 0, right? So after this step, you have to equate the least powers of x in order to get that indicial equation, or you call it auxiliary equation, to get the values of r, right? So you can see that the least powers of x from the first term will be x to the power r, that will be obtained by plugging n equal to 0 here, right? And from this term, if you plug n equal to 0, you will get x to the power r, that is also correct. But from the third term, if you put n equal to 0 here, you will get x to the power r plus 2. It means that from the third summation, you are not going to obtain any x to the power r term, right? And see the fourth term, here also you are getting x to the power r. So ultimately, in order to get the least power of x, that is x to the power r, only three terms are contributing, right? The first term, second term, and fourth term. So equating coefficients of x to the power r, right? That is the least power of x in order to get the indicial equation. Comparing any other power of x will not give you indicial equation, right? So from the first term, on putting n equal to 0, I will get a naught r minus 1, right? And from here again, you have to put n equal to 0, so we will get a naught multiplied with r, right? From the third term, you are not getting anything. Terms like x to the power r are not present in this summation, right? So going to the fourth term, minus p square and a naught equal to 0, right? And at this point, you can see that you can take this a naught common, so that will produce a naught will be taken as common, and inside bracket we will be having r square minus p square equal to 0. And again, this is very important step, because there are two factors in product, right? So in order to get the indicial equation, you need that this a naught should be not equal to 0, and that is indeed the case. We have assumed at the beginning that a naught is not equal to 0, right? And this is the importance of this constant. It cannot be equal to 0. If you assume it to be 0, then you cannot have an indicial equation, right? So you know that a naught is not equal to 0. So you can always write that r square minus p square equal to 0, as we have already mentioned that a naught is not equal to 0, right? Okay. So from here you will get two values of r. One is p and other one is minus p, right? So you have two values of r, or should I write it as r1 and r2? r1 equal to p and r2 equal to minus p, right? Okay, so you have two values of r, and now you will equate the next power of x, that will be the x to the power r plus 1, right? So equate coefficients of x to the power r plus 1, right? And from the first term, if you want to obtain x to the power r plus 1, then you have to plug n equal to 1 here, right? So plugging n equal to 1 in the first summation, you will get a1 1 plus r, and this will be r, right? And from here, if you want to get x to the power r plus 1, you have to plug n equal to 1, that will produce a1 1 plus r, right? And third summation is not going to give this term x to the power r plus 1, because if you put n equal to 0, then you are getting x to the power r plus 2, that is higher than this thing, right? So from the third term, there is no hope of getting this term, right? So leave that third term again and go to the fourth term, that is minus p square, and from here you have to put n equal to 1, and in that case you will have a1 equal to 0, right? And now again you can see that you can take this a1 common, and that will produce a1, and here you will have 1 plus r common from these two terms, and r plus 1 again, and that will become 1 plus r whole square and minus p square. So you can write it as 1 plus r whole square minus p square on simplification, right? And now comes the important point. Yeah, because you have two factors in product, right, and you want to get 0 result. So which of these two will be 0? Either a1 will be 0 or this will be 0. We know that this term cannot be, this factor cannot be equal to 0. Why? Because the value of r is either p or minus p. If you put r equal to p here, then you will get 1 plus p whole square minus p square. That is obviously not equal to 0 in any case, right? And if you put r equal to minus p here, you will get 1 minus p whole square minus p square. That is again not equal to 0. That will be something like 1 minus 2p, I think. Okay, so in any case, for these two values of r, this factor is not equal to 0, right? It means that a1 equal to 0, right? I am repeating it again. This factor cannot be equal to 0 because r plus 1 is not equal to p. Obviously, if r plus 1 becomes equal to p, then this will go to 0, right? R plus 1 equal to p means r should be equal to p minus 1, but that is not the case. Actually, r is equal to p, not p plus 1, right? That's why it cannot be 0. So a1 has to be 0. There is no choice, right? So implies a1 equal to 0, as you know that r plus 1 is not equal to p, right? Since we already know that the values of r is p or minus p, right? So be careful at this point, right? So a1 is equal to 0. Okay. Then what I will do, I will try to equate the highest visible powers of x, because I want to get the recurrence relation, and in order to get the recurrence relation, to find the higher coefficients an plus 1 and so on, you have to equate the highest visible powers of x from this equation, right? So if we see this equation, then all of these, there are 4 summations, right? And the highest visible power of x is this much, x to the power n plus r plus 2, right? And yeah, and obviously these 3 summations, first, second and fourth summation, they are also containing the terms x to the power n plus r plus 2, because these summations are running up to infinity, right? Be careful at this point. Do not overjudge this situation. X to the power n plus r plus 2 is visible in the third summation, but these terms also appear in first, second and fourth summations, right? So I will equate the highest visible power, that is x to the power n plus r plus 2, coefficient of x to the power n plus r plus 2, right? And now I will come to the first summation, right? If you want to obtain x to the power n plus r plus 2, right, so you have to put n equal to n plus 2. If you replace n by n plus 2, you will get x to the power n plus 2 plus r, right? So I will do that, and from here I will obtain n replaced by n plus 2 in the first summation, right? That will produce a n plus 2, right? N plus 2 plus r, and n plus 2 plus r minus 1, that will be n plus 1 plus r, right? N plus 1 plus r, right? This is the first summation. And from the second summation, you have to again replace n by n plus 2, yes, and that will produce a n plus 2, n plus 2 plus r, right? And yeah, third summation is very easy because it is already here, this term x to the power n plus r plus 2, and the coefficient is an. No need to do any replacement, plus an, right? And the last term, in order to get x to the power n plus r plus 2, I have to replace n by n plus 2 equal to 0, right? And now you have to pair the like terms, like you have an plus 2 in these 3 terms, 1, 2 and 3, the first, this one, second and third. So I will take an plus 2 common out of these 3 terms. So first I will do it this way, that taking an plus 2, right, common, and you can see that this n plus 2 plus r is also common in these 2 terms, right? And if you take this n plus 2 plus r common in these two terms only, then you will get inside bracket n plus 1 plus r plus 1, and that will ultimately become n plus 2 plus r. So finally it will become n plus 2 plus r whole square, right? So be smart while simplifying these recurrence relation, because on multiplying these factors and then trying to express n plus 2 in terms of n, that will be quite messy. So be smart at these steps, right? So what I will do, I will focus on just these two terms, right? And I can take a n plus 2 common. You can see that a n plus 2 is common, right? And n plus 2 plus r is also common, and inside bracket we will be having with n plus 1 plus r plus 1. That will ultimately become n plus 2 plus r whole square. I hope that you understand this thing, right? And now this term an can be taken on the right hand side, and this is minus p square an plus 2 equal to negative of an. Now we can take an plus 2 common, and that will produce an plus 2 equal to negative of an divided by n plus 2 plus r whole square minus p square, right? This is the recurrence relation, is recurrence relation, right? And using this relation, I will try to obtain the values of the next coefficients a2, a3, a4 and so on, right? So I will be using this, and first I will put n equal to 0 in order to obtain a2 in terms of a0, right? So put n equal to 0 to get a2 equal to minus of a0 divided by, put n equal to 0, then you will have 2 plus r whole square minus p square, right? This is a2. Putting n equal to 1 will give you a3 equal to minus a1 divided by how much? 3 plus r whole square minus p square, right? And since you know the value of a1 was calculated here, a1 was equal to 0. So using this value, this will go to 0, right? Right. So it appears that all odd coefficients will be 0. Similarly, a5 will be 0 because that will depend on a3. a7 will depend on a5, right? So all of them will be 0. So now I will put n equal to 2 here to get a4 in terms of a2. Yeah, and I have substituted n equal to 2, so that will become 4 plus r whole square minus p square, right? And again using this value of a2 is this much, so plugging that value, that will become plus sign, and here you will have 4 plus r whole square minus p square, 2 plus r whole square minus p square, right? And for n equal to 3, you will have a5 that will use a3, and in the denominator you will be having 5 plus r whole square minus p square, but that will go to 0 since a3 is equal to 0, right? And last, n equal to 4, a6 equal to minus of a4 divided by how much? 6 plus r whole square minus p square, and using the value of a4 from here I will get, I think that will be negative, yeah, minus a0 divided by 6 plus r whole square minus p square multiplied with 4 plus r whole square minus p square, and further multiplied with 2 plus r whole square minus p square. So 6 coefficients are sufficient. Okay, and yeah, now I will plug these coefficients here in my equation. Where is that? So this is my solution. I will call it equation number 2, right? This is my equation number 2. I will plug all of those coefficients in equation number 2, right, in order to get the solution. So plug these ai's, right, where I is equal to 0, 1, 2 and so on, right, in equation number how much? 2, right? So that will give you y is equal to x to the power r, right? And you know that these odd coefficients are 0, so I am not going to write them. A1x is 0, a3x square will be 0, and so on, right? So you can see that a2 is depending on a0, right? Similarly, a4 is depending on a0, so I will take a0 common, right? So here I take a0 common out of all the terms inside bracket. So first term will be 1 because a0 has been taken common. A1 is 0, a2, where is a2? Yeah, minus x square divided by 2 plus r whole square minus p square, right? And then a4 plus x to the power 4 over 4 plus r whole square minus p square multiplied with 2 plus r whole square minus p square, right? In the last term, minus x6 divided by 6 plus r whole square minus p square, 4 plus r whole square minus p square, and 2 plus r whole square minus p square, right? And so on, plus so on. So this is a solution in terms of r, right? However, the values of r are still remaining to be substituted here in the solution, right? So that will be going to case 1 and 2, right? But this is a solution. You can say that this is a solution of that equation number 1, Bessel's differential equation, and this is involving r, right? Obviously it is involving p because the original differential equation was involving p, and the different values of p will produce different cases, two cases, case 1 and case 2, right? So I have to rub this first, but you have to remember this differential equation at least, right? Okay. So on plugging r equal to p here in that solution, you will get y equal to a naught x to the power p 1 minus x square divided by 2 plus p whole square minus p square. That will become p plus 4 times 2, right? 2 plus p plus p, sorry, 2p plus 2. That will become, I think, 2p plus 2 and multiplied with the 2, right? And next term will be x to the power 4 divided by 2 and 4 and 2p plus 2, right? And from there you will get 4 plus p plus p, that is 2p plus 4, 2p plus 4, right? So your series will be like this. I am not writing the next terms, right? I have to generalize it from here. And now you can see that you can write it as, if you take this is 2, okay, I will leave this first. First I will write this term. See here, these are two factors, and you can take 2 common of these two, so ultimately that will be 2 square, and from here, from these two, you can take 2 square common, so 2 square will be common, and you will be left with 1 and 2, because these are product terms, and when you have product terms like 2, 4, 6 in product, then you can take 2 to the power 3 common, right? The number of terms appears in the exponent, right? So that's why we have 2 terms, and from both of them are multiples of 2, so 1, 2 common from this term, 1, 2 common from this term, collectively it will become 2 square, and inside bracket we will be having 1 dot 2, and that is actually 2 factorial, right? And from here you can take 1, 2 common, 1, 2 common, again that will club to 2 square, and that will be added to this thing, that will become 2 to the power 4. So it is tricky, right? P plus 1 and p plus 2. I think we are done now, and just now to focus on this term, this will be I think 2 square, 2 square and 1 factorial, right? And p plus 1, right? And you can write the next term also, minus x to the power 6 based on the same pattern, Since the power is 4, 2 to the power 4, so 2 to the power 6, and we have 3 factorial here, and p plus 1, p plus 2, p plus 3, and so on, right? So this is the solution, is a solution of Bessel's equation that was numbered as first equation. So this is a solution, and it is involving p, right? So the solution is this much. First solution only, not the second solution. The second solution is still remaining for this value of r, that is minus p. So here comes the theory of Bessel's function, right? So be careful after this point. We have to do some manipulations in order to achieve that Bessel's function, right? That looks quite ugly. So in order to achieve that Bessel's function, this is the solution of Bessel's equation, but I am going to obtain Bessel's function, and I have to do slight modification on this solution. Slight modification in the sense of this constant. You can see that this whole solution is containing just one constant. This is a naught, right? And the choice of a proper constant produces Bessel's function. This is not the Bessel's function. This is the solution of Bessel's equation, right? Similar to the case of Legendre's function, as we did in our last video. Okay, so what I will do, I will write this whole series in summation form first, in closed form, and then I will try to do some manipulation, right? So what I will do, I will just write this series inside the bracket, right, in this way. See, summation, right? If you pick up any term, do not pick up the first and second term, just see on the third term. This is a good term in order to get a generalized term, right? So see the third term. This is the third term. Okay, this is x to the power 4, right? And you can see that all powers are even powers. The first thing is that. So if you focus on this term, I will put a dot here for this term, right? So this is x to the power 4, that is of the form x to the power, and x to the power 4 and 2 to the power 4, x to the power 6, 2 to the power 6. So you can say that x to the power 2n and 2 to the power 2n, because both x and 2 have same powers, right? And why I use n? Why not the other variable k, t, right? Because see here, I have dropped that actually. Our suffix was n in all cases, right? I have used the Frobenius series that was involving summation, and that was a n x to the power n plus r. N was the index for summation, right? So remember that the same index we used in the Frobenius series, that will be used here. N, not r, not k, not any new variable. You have to use n, right? So n equal to 0 to infinity, right? If you put n equal to 2, you will get this term, right? Okay. And see here, this is 2 factorial. It indicates that this should be n factorial, I think, yeah. And this p plus 1, p plus 2, that will run up to p plus n. And you can verify that by actually putting n equal to 0 here in this whole term. You are getting this term, yes or no? If you put n equal to 0, you are getting 1, okay, 1, p plus, what is that? P plus 1, sorry, n equal to 0. So n equal to 0 will not produce any of these factors, because the last is p plus 1, right? If you put n equal to 1, you will get x square, 2 square, 1 factor p plus 1. Yeah, fine. Putting n equal to 0, 1, 2, 3 is putting in this series. So this is a generalized summation form of this solution, right? And now comes the twisting point. You have to choose this a naught in such a way that choose a naught equal to 1 over this is p plus n, this is 2 to the power 2n, and this is actually this x to the power p can be added here. You can see that I am rubbing it here, and this will become 2n plus p, right? And you want that this 2 must have the same power as this x. So here I should have 2n plus p. So plus p is missing. 2 to the power p is missing in the denominator. So I have to balance it and multiply and choose this constant in such a way that I will achieve my goal. I want that this will be a single term, x by 2 whole to the power 2n plus p. And in order to achieve that goal, I should use a not equal to this much, because you know that you can play with constants. If you have some solution, that is y, you can multiply that solution y with any constant to get a new solution, right? So changing a constant will not affect the solution. The solution will still be a solution, right? So you are changing a naught, you are choosing a particular a naught, right? And why we are choosing that, I will explain it later. So first is this, you are multiplying with 2 to the power p in order to get the same powers of x and 2 in the denominator. The first thing is that. And you can see these too many factors are there, so much factor, p plus 1, p plus 2, p plus 3 and so on. I want this whole thing in factorial form, right? So what you will do, you will choose, if you see it in reverse way, p plus n minus 1, p plus 2, p plus 1, and it should go up to 3, 2, 1. So what is missing? The missing thing is p factorial, right? So if you multiply, if you choose this a naught this much, then this summation form will not look ugly, right? It is looking very ugly due to the presence of these odd terms, right? This power of 2, right? So in order to achieve some beautiful summation form, you have to put the substitution a not equal to this much, right? Okay. In order to get Bessel's function of first kind of order p, denoted by jpx, right? So using this value here, and finally I will replace that y with jpx equal to, now you can see that if you use this constant, then this summation will be written in this way, and equal to 0 to infinity x by 2 to the power 2n plus p, right? The first thing is that you can write these x and 2 together because they have the same power. Now we use this a naught, and this p factorial multiplied with this whole thing, that will produce p factorial, and p plus n factorial, right? So you have to remember this at least. This is called the Bessel's function of first kind of order p, right? And you can see that inside the summation, here you have p, right? And here you have p plus n, p factorial, right? However, the summation is running for the index n, right? So this is the first Bessel's function of first kind, right? And indeed, this is also the solution of differential equation 1, because by changing a constant, a solution will still be a solution. So Bessel's function is a solution of Bessel's equation, obviously, right? Okay, I have to rub it first. Now comes the discussion on the behavior of p. As you know that p is a non-negative constant, so it can be any integer or a non-integer, because you have the values of p from 0 onwards to the positive side. This is 0 to infinity. P belongs to 0 to infinity, positive side. P is non-negative. So we can classify the values of p as an integer value, and p is a non-integer. There are two cases, right? So I will take the first case, case 1. Case 1, if p is a positive integer, is a non-positive integer. P is a non-integer, obviously positive, right? Okay. Then the second solution can be obtained by replacing p by minus p in jpx, right? So if you remember that you have two values of r, there is first one was p and the second one was minus p, right? And you can see that they are distinct values, right? If they are non-zero, p is different from minus p, and you have already obtained the first solution. It's called the Bessel's function of first kind of order p by using the first value of r, that was p, right? And what is remaining? The second value of r, that is minus p. So what I will do, I will just use this value minus p, right, in my solution. Here you can use this in place of r. In place of r, you can put that r equal to minus p in order to get the second solution. But rather than writing this and doing the same thing again and again, why don't I just replace this p by minus p here, because everything will be same, right? And indeed that will be accepted as a second solution. Why? Because that will be the independent solution from this jpx. We call two solutions as independent solutions if they are not the scalar multiples of each other, right? Or you can say that if their ratio is a non-constant, right? So we claim that if we consider p as a non-integer, right, then the second solution, that is written by j of minus px, right, will be the independent solution from this first solution, right? And I will show that the second solution can be obtained with p in minus p, okay, that is j minus p x. I am just replacing that p by minus p, and this replacement is possible if and only if this p is a non-integer, right? Summation n equal to 0 to infinity, and x by 2, you can see that here we had 2n plus p, so now I will have 2n minus p divided by, and yeah, here you have p factorial. I think I have missed something. It should be n factorial. Yeah, n factorial. Okay, n factorial. N factorial, and you have minus p plus n factorial, right? So this will be your second solution, right? Okay, and you call it Bessel's function of second kind of order minus p. I will write that. Bessel's function of second kind of order minus p, right? Okay, so we claim that this solution should be accepted as the second solution because it is independent of that first solution, right? So we have to prove that. How we can say that this is independent? By just looking at this solution? No, right? We will investigate just the value of this j minus px at x equal to 0, just one point, right? Clearly j minus p at 0, I am putting x equal to 0, right? We put x equal to 0, and this is indeed an infinite series, so I should write it this way. Clearly the first term, I am focusing on the first term, clearly the first term in j of minus p x, if you try to obtain the series from this, if you put n equal to 0, so you will get x by 2 to the power minus p. Just focus here. If you put n equal to 0, you will get x to the power minus p. That is sufficient. So x to the power is minus p. You have to write it x to the power 1 by x to the power p. And if you put x equal to 0 there, you will get infinity, right? So clearly the first term in j minus px is, I will write that first term, that will be 2 to the power p, x to the power p, and you have replaced n equal to 0, so that will become n factorial whole square. No, you have put n equal to 0, sorry, n equal to 0, so this is 0 factorial 1, 0, and this will be minus p factorial, and minus p factorial has no meaning, right? You know that negative factorial or fractional factorial is not allowed. You convert it into gamma function, right? So I should write that minus p factorial can be should be written as minus p plus 1, gamma of minus 1 plus p, gamma of minus p plus 1, right? You just have a formula, gamma n plus 1 equal to n factorial. Like 5, gamma of 5 is equal to 4 factorial. Gamma 100 equal to 99 factorial, right? So I have to write gamma here because I know that negative number don't have factorial, or you can say that fractions don't have factorial, right? They have gamma function, right? So this will be a first term. Clearly, the first term in this is unbounded near x equal to 0. If you put x equal to 0 here, you are getting infinity. So I have to use this word unbounded. Going to infinity means unbounded, right? But j p x is equal to 1 at x equal to 0, right? You can see that. Put x equal to 0 here, and first you have to write it in expanded form. This is written here. This is the expanded form. You can see that. If you put x equal to 0, all of these terms will go to 0. You will be left with 1 and a naught, and a naught is chosen in such a way that the first term will be 1. You should write it in expanded form first, and then put x equal to 0. You will see that jp0 is equal to 1. But j minus p0 is how much? Infinity. It means that at x equal to 0, the first solution jpx was achieving the value 1, but the second solution is going to infinity, right? So at the same point, one solution is at different point 1, and the second solution is towards infinity. It means that obviously they are independent solutions, right? Because the dependent solutions just overlap each other, right? Okay, so we can say that hence j minus px and jpx are independent solutions, right? So at this point we accept that yes, this is the second solution and it is a linearly independent solution of the jpx. So the complete solution should be written as y is equal to constant multiplied with the first solution that we call jpx, that is a Bessel's function, right? And plus b times the second solution is the solution when p is a non-integer. P is a non-integer, right? So this is a solution. And now I will go to case 2 when p is an integer, and we'll see that in that case whether this j of minus px will be independent from the first solution, right? We have to check that. We'll first write this j minus px as we have written here, and we have to investigate, at least we have to take x equal to some point, that whether they are showing the different values as these two solutions are showing, in order to write that this is indeed the second independent solution, right? So I have to rub this first. Okay, so case 2, I should write it from here, I think. Case 2. Case 2 is if p is an integer, obviously positive integer because p is non-negative, right? So p is an integer, then if we write this j minus px, right, then j minus px will be equal to summation n equal to 0 to infinity and x by 2 to n minus p divided by n factorial minus p plus n whole factorial, right? This will be the j minus p, but we cannot say that this is the independent solution. We have to check that, right? And remember that the difference in these two cases is that this time your p is an integer, right? Okay, so I can write this summation in this form also. You can see that if I break this summation into two summations like this, the first one running from n equal to 0 to, here you can see that this is n minus p, so n will run to p minus 1, of p. At p it is becoming, if at n equal to p it is going to 0, and that will be here. So p minus 1, and from here n equal to p to infinity, right? So I have broken this summation into two summations. We can do that, and you can see that I have broken this summation. After watching this thing, you can see that this is minus p plus n. At n equal to p, it is going to 0. If you put n equal to p, it is going to 0, and 0 factorial is equal to 1, and that is defined. So I have taken that here, right? And from n equal to p onwards, all factorials are defined, right? And before n equal to p, we have n equal to p minus 1, and the summation is starting from n equal to 0. So I have written that summation here, right? So that thing is x by 2 to the power 2n minus p divided by n factorial minus p plus n factorial, right? And here the same thing, plus x by 2n minus p divided by n factorial minus p plus n factorial, right? And if you write the terms of this summation in expanded form, you will see that if you put n equal to 0, just focus on the denominator, right? If you put n equal to 0, that is fine, 0 factorial, that is defined. But inside bracket we will be having how much? Minus of p factorial, right? And what is p? P is an integer and positive integer. So minus of p factorial will be a negative factorial, because p is positive, p is not negative. So we will get a negative number factorial, right? And the negative number factorial is equal to minus infinity, right? Like minus 1 factorial is equal to minus infinity, minus 2 factorial is minus infinity. All factorials of negative integers are equal to minus infinity. You have to remember that point. And due to that fact, all of these terms will go to 0, because in all of these terms you will have minus p factorial, minus p plus 1 factorial, minus p plus 2 factorial, and all the denominators will be containing the factorial of negative integer, right? And in all the denominators you will have minus infinity, and since you have minus infinity in the denominators of all of these terms, all of these terms will go to 0 ultimately. So I will write that 0 here, right? And you should know the reason why it is 0, because the factorial of a negative integer is equal to 0, right? And we are left with this thing, plus summation n equal to p and summation x by 2n minus p divided by n factorial minus p plus n factorial. Note that here you cannot have a negative factorial, because n is starting from p. If you put n equal to p, you will get 0 factorial, that is 1. If you put n equal to p plus 1, you will get 1 factorial, that is 1, right? So that situation is not happening here, right? So you are left with this, because this is 0, okay, you are left with this. And if I replace this n, because you can see that the summation is starting from n equal to p, and if you want that, generally the range of the summation starts from n equal to 0, if you want that, right? So we can always put n minus p equal to a new constant, let it be k, a new index I should say, not a constant, because here the index is n and that is starting from p, but you want a new index that starts from 0, right? So you have to take this p here in the left hand side, so that it will become n minus p equal to 0. So you will use n minus p as a new index, that will be k, in order to obtain some general results, right? So replace n minus p by k, and this k is a new index, right? That will start from 0 to infinity. So what will happen? This summation, it was j of minus p x equal to this summation, the lower range will be n minus p, was n minus p, and it will become now k equal to 0 to infinity, right? And this x to the power x by 2 whole to the power 2 times the value of n is p plus k, so I will write that p plus k, and where is that, minus p. So ultimately on solving it I will get how much? 2p plus p plus 2k, I think, p plus 2k, 2k plus p, if I'm not wrong, right? I think I have missed something, and a very big point. I have missed that sign, right? See that here you had negative, positive, negative, positive, negative. So I have completely missed that point, and I should have minus 1 to the power p here. Yeah, minus 1 to the power p. Yeah, 0, p or 0, minus 1 to the power n, I think. N. If you put 0, positive, 1 negative. That was a big mistake, so that should be corrected here also. Minus 1 to the power n, and here also minus 1 to the power n, and there's that here. Minus 1 to the power n, right? So be careful by generalizing a series, right? So take care of these signs also. The sign was also fluctuating, and I completely missed that, right? Okay, so here I had what? Minus 1 to the power how much? N, and n is replaced by p plus k. So that will be p plus k divided by n factorial, and n factorial can be replaced by p plus k factorial. Yes, and here we have n minus p, there is already k factorial. So this is my new j minus px, right? Remember that what we are trying to do, we are trying to seek the second independent solution, and this time p is an integer, and we are focusing that whether this j minus p is able to be taken out as a second solution or not, right? So j minus px is this much, and you can see that you can take negative minus 1 to the power p common. Yes, yeah, minus 1 to the power p can be taken outside, right? Because the summation index is k, not p, so you can take this outside, and this summation k equal to 0 to infinity, and this is minus 1 to the power k will be left inside bracket, and x to the x by 2 to the power how much? 2k plus p divided by k factorial p plus k whole factorial, right? And yeah, if you compare this thing, I will put a bracket here, if you compare this whole thing, this summation with this, where is that? jpx, they are exactly the same. Only one difference is there. The index was n, and here the index is k. However, they are identical, I think. Yeah. So I can replace this by jpx again, right? The index is immaterial, right? Index is just for notation. You have to obtain a series, and in that case, k will be absent, right? So I can replace this whole thing by jpx, right? That will be minus 1 to the power p j of p x, and here we had j minus p x, right? And now you can see that this j minus p x is actually a scalar multiple of jpx. So we cannot say that j minus p is an independent solution. No, it is depending on jp, because their ratio is a constant. You can see that if you take this here, if you take in the denominator, then the ratio will be minus 1 to the power p, and minus 1 to the power p is a constant, right? So this time when p is an integer, this j minus p is not going to work as your second independent solution, right? We have to do something else in order to get the second solution. So after reaching this point, that is j minus px is a scalar multiple of jpx. Therefore j minus px is not a second solution, right? We have to do something else, and to seek that second independent solution, when we already had a first solution, right, jpx, I will use the theory of differential equation of order 2 that we did in our last semester course, right? I will write that formula directly. Okay, so in order to get the second independent solution, right, let it denote it by y2, right? Y2. Use the result. I will write that theory first, right? A small part of theory, like this. Use y2 is equal to vx multiplied by y1, right? And what is the y1? Y1 is jpx, the first solution, right? And where vx is given by this beautiful formula, e to the power minus integration px dx over y1 square dx, right? So I will use this fact. This fact comes from the last semester course, theory of differential equation, right? For the ordinary differential equation, that was a standard differential equation of this type, y plus qxy equal to 0, right? So I will be going to use this thing here in my Bessel's equation for this case number 2. And in my case, my y1 is actually that jpx. And what do I need? I need here, see this formula, I need px here. Px was the coefficient of y dash, and I have rubbed that differential equation, Bessel's differential equation, and the coefficient of y dash was 1 upon x, right? So I'm going to use that. That is, the second solution will be the value of vx is this much, so I will write that value. The value of y1 is, what is the value of y1? Y1 is jpx, jpx multiplied with vx, and the value of vx is this much, so I will writing that value, e to the power minus integration px, and px in my differential equation, in Bessel's differential equation, is 1 upon x dx over y1 square, and y1 is in my case jp, so jp square x dx, right? Note that I have done this in one step only, right? I am mentioning what is my y1 jp, and I have used that px, the coefficient of y dash, that is 1 upon x, right? Now it remains to integrate this. You can see that the integration of 1 upon x is log x, and that will go in the power, then 1 by x. Ultimately I will get this thing, jpx integration 1 over log x, 1 over x, yeah, 1 over x multiplied with jp square x dx. This is the y2. This is your second solution, right? Yeah, and now we'll write the full solution, right? Full solution can be written as a constant times multiplied that first solution plus constant times multiplied with this second solution, right? So this is for case 2, right? And now we'll write few remarks about this thing, right? Okay, so writing remarks, right? The first remark is about this jpx. Where is that jpx? I will write from here. Remark number 1: jpx equal to summation n equal to 0 to infinity minus 1 to the power n x by 2 2n minus p, sorry, 2n plus p, it should be, divided by n factorial and p plus n factorial, right? So this was your first solution, Bessel's solution, Bessel's function of first kind of order p, right? And practically J0x and J1x are important, right? So if I plug 0 in place of p, I will get summation n equal to 0 to infinity minus 1 to the power n, and you will get x by 2 to the power 2n divided by n factorial whole square, right? This is j naught x, and you can always write this in expanded form, and it will become, if put n equal to 0, that will become 1 1 1, yeah, the first term will be 1, second term will be negative, and 1 will become 1 factorial, okay, and x by 2 whole square. So x square by 2 square. If you put 2, that will become plus 1, and 2 factorial whole square, 2 factorial whole square, and x to the power 4 or 2 to the power 4. So the series goes like this. So this is j naught x, right? And similarly, if you put j1, means p equal to 1, you will get summation n equal to 0 to infinity minus 1 to the power n x by 2 2n plus 1 divided by n factorial, and this will be n plus 1 factorial, right? And if you write this summation in expanded form, then the first putting n equal to 0 will give you x by 2 0 1 factorial, yeah, x by 2, and yeah, x by 2 I think only, n equal to 0, yeah, x by 2, right? And second term will be negative, yeah, 1, so that will become 2 factorial I think, yeah, 1 factorial 2 factorial, okay, 1 factorial 2 factorial, and negative is here, so x to the power 3 cube over 2 cube, right, and so on, right? You can see that all of those terms are containing x, right? This is a j naught, this is a j1, right? And you can see that if you put x equal to 0 here, so j naught 0 will be 1, but j1 0 will be 0, right? Clearly, j naught 0 is equal to 1 and j1 0 equal to 0, right? So actually I'm going to draw their graphs. These functions j naught x and j1 x are of practical importance, right, as they are bounded, right? So I will try to graph them, and the graph is like this. This is 1 1 2 3 4 5 6 7 8 and so on. Okay. This is the x-axis. And if you plot this j naught x, their graph is sinusoidal in nature, like that of cos x. J naught x has graph similar to cos x, and j1 x has graph similar to sin x. Due to these facts, you can see that cos 0 is equal to 1 and sin 0 is equal to 0, so their graph are similar, except the fact that sin has a fixed amplitude 1 and minus 1, but they have decaying amplitude. They goes on decaying, their amplitude goes on decreasing as they move towards infinity. So if this is 1, then drawing the graph of j naught x, it will start from here, and it has zeros, if I remember, then 2.5, nearly 2.5, yeah, like this, 2.5 and then 5.5, like this. And since the amplitude is 1 here, now it will go on decreasing, and then 5.5, then 8.5, nearly 8.5. The amplitude will go down like this, right? You can see that the amplitude is bigger, and as it goes towards infinity, the amplitude goes on decreasing. This is a graph of j naught x, and similarly the graph of j1 x, since it starts from 0, and it will go like that. Right, so this is the j1x, and you can see that their zeros fall alternatively. It means that between any two zeros of j naught, you can see that these are the zeros of j naught. the point where it is crossing the x-axis, there exists exactly one zero of J1, right? And similarly, between any two zeros of J1, there exists only one zero of J0. Similar to the behavior of sine and cos. Like in sine, between any two zeros of sine, there exists a single zero of cos, and vice versa for the cos also, right? So these are the graphs, and now we'll write the final point. Remark number 2, and that is the standard Bessel's function of second kind is defined as ypx equal to jpx cos p pi minus j minus px divided by sine p pi, right? This is the standard Bessel's function of second kind. It is defined in this way also. And why it is defined in this way? Because this is indeed the solution of differential equation, Bessel's differential equation. Why? Because I have rubbed that. Our solution was of the form capital A times jpx plus capital times b times j minus px, means a constant multiplied with jpx and another constant multiplied with j minus px, right? That was the solution, and this is indeed the same thing, right? You can see that if you write these terms in this way, this upon this and this upon this, the first term will be cos upon sine or cot p pi multiplied with jpx, and the second term will be 1 upon sine minus 1 upon sine p pi multiplied with j minus px. So in this standard Bessel's function of second kind, the first constant, there is a coefficient of jpx, that was capital A. In our case, as I have written here, I have written that here, that is cot p pi, right? And in place of capital B in our solution, they have minus 1 upon sine p pi. So indeed that this will be a solution, because taking any pair of A and B, a solution will still be a solution. That's why it is a solution. And choosing these special magical constant cos p pi sine p pi, that is a part of research, right? You can refer to several research papers how it appeared, and that will be a long proof for 20-30 pages, right? So you have to remember that this is a standard Bessel's function, but that is not needed actually. The second solution was indeed given by j minus px. There is also a solution, and this is also the solution in case of integers. P is an integer, right? So it is just for reference. You should know this, that this is a standard Bessel's function of second kind, right? However, this is not used. The problem with this thing is that it is unbounded near x equal to 0. For practical importance, you need those solutions which are bounded, right? But this second solution, this second kind solution of Bessel's function is unbounded near x equal to 0, so it is not of practical importance, right? Only jpx is important, right? So this is a standard Bessel's function of second kind, right? Okay, and again, or also, if I write y is equal to capital A jpx plus capital B ypx, note that this is a yp, right, is solution whether p is an integer or not. This is an important point, because it will be a solution in both of cases. Case 1 when p was not an integer, and case 2 when p was an integer. So it works well in both cases, right? So this is it for this video, the solution of Bessel's equation. In the next video, we'll investigate some properties of these Bessel's function, especially Bessel's function of first kind, jpx, right? That will be part of next video. For this video, thanks.